So there are three types of subatomic particles in the atoms, right? We have protons, electrons, and neutrons, and we're going over things that are general, like your three types of subatomic particles and how to quantify those using the periodic table. And so we're going to look now into more detail the electrons. Okay? So the electrons, how they behave, some properties, and then we're going to look at where the electrons are located in the atom. So specifics of the atomic structure. And we are looking at the electrons specifically into more detail because the electrons, you will learn that they are responsible for the bond formation. So you know, when you have two or more different types of atoms combined, chemically bonded, you're getting compounds. So compounds are classified into different types of compounds based on the chemical bonds that they're forming, and those bonds are formed between electrons when the electrons are shared or the electrons are transferred. And also electrons are responsible for reactivity of different substances. So that's why we're going to spend some time looking at the electrons. So the quantum mechanical model of the atom, it's something that it's a mathematical model, and it's used to explain like how the electrons exist and the behavior of the electrons. So the electron, it can be described using properties of matter and also using properties of waves. And we have this wave-particle duality. So a wave can be described based on different properties like wavelength, frequency, and energy. And we have different symbols for each one. Okay? We have wavelength, frequency, energy here, and we can go over the relationship between energy and wavelength, energy and frequency. There are mathematical equations that relate the properties. We're not using the mathematical equation to solve any mathematical problems. Okay? We're just looking at the equation to determine the relationship between two different properties. For example, in the first one, energy and wavelength, in that equation you have two constants here, h and c, which are Planck constants and the speed of light, and you have the numbers here. And so just looking at the equation, you can see that the numerical values of your constants, they are multiplied times each other, and then that number is divided by the wavelength, and when you solve that, you're getting a value for the energy. So the number is divided by the wavelength, which means that if this number down here, it's increasing, the numerical value that you're getting for the energy, it's decreasing. And that tells you that the relationship between energy and wavelength is inversely proportional. So that means that if the wavelength is increasing, the value of the energy will be decreasing, or the other way, it's also true. As the wavelength gets shorter or decreases, the numerical value for the energy will be increasing. And then we have another mathematical equation here. Energy equals the Planck constant times the frequency. So in this one, the frequency is multiplied times your Planck constant, and that gives you the numerical value of the energy. So the relationship between energy and frequency, we can say that is directly proportional. As the frequency value increases, the energy value also increases, which means that the other way around, it's also true. If the number for the frequency is decreasing, the numerical value for the energy will be also decreasing. There are different types of electromagnetic radiation, and we can organize electromagnetic radiation using that property of wavelength. Okay? So depending on the range of wavelength that you're looking at into this spectrum here, you're going to have different types of radiation. So we're going to be focusing on this part here of your electromagnetic spectrum, where you have the visible part. In the visible part, we have a range of wavelength that is between 400 and 700 nanometers. And those numbers are not exact numbers. Okay? I'm approximating those numbers in a way that it's easy for you to remember. So depending on the source that you use or book, you will see that these numbers that I'm writing here are kind of different. So here I'm organizing my different types of radiation in a specific order. Now I have a note here that says that gamma rays, X-rays, and ultraviolet rays, they are highly energetic. So you have enough energy that those type of radiation can actually damage biological molecules. I'm sure that all of you have heard about ultraviolet radiation, which comes from the sun, and we're always encouraged to use sunscreen when we're getting exposed to the sun, and it's to protect us from this ultraviolet radiation, which can damage biological molecules. So if these three here, they have a high numerical value of energy, we can trace a trend. So if we have high energy up here, it means that the energy is increasing as you move from here up. So that's why my first arrow here, it's represents that the energy is increasing. Now the second one right here in the middle, it's also pointing up. So I have three properties listed. I have energy, wavelength, and frequency, and we went over the relationship between energy and wavelength, energy and frequency. So if the energy is increasing, moving up here in your electromagnetic spectrum, your energy and the frequency, they are directly proportional. If one is increasing, so does the other, which means that my middle line here represents the frequency, because it's increasing in the same direction as the energy. And then I have my third arrow here representing my third property, which is the wavelength. So the wavelength, it's increasing in the opposite direction as the energy and the frequency, because wavelength and energy are inversely proportional. So frequency and energy increasing, going in that direction. And then down here we have the wavelength increasing. The numerical value is increasing for the wavelength. So you can actually organize your different types of radiation based on increasing wavelength or increasing frequency, increasing energy, which is something that we're going to do in one problem later. Now, the visible part of the electromagnetic spectrum is what we can actually see. We can see anything that is contained between this range of wavelengths that I'm listing down here, 400 and 700. Now, you can see the relationship between your energy and the wavelength, that they are inversely proportional. So in the visible part, I'm listing here the colors, starting with the violet, which is the one with the higher value of energy associated to, going down to the red one, which is the one with a lower value for energy associated to. So for your colors here contained in your visible part of the electromagnetic spectrum, we can also use my three arrows here to see what's happening with those three properties: energy, frequency, and wavelength. And I have my diagram down here, and it's representing exactly the same thing that you have here. All of these represent the visible part, and I have my colors with wavelengths associated to them. I have starting in 400 going to 450 my violet. You have a shorter wavelength or a smaller numerical value for the wavelength for the violet color, because that's the one with a higher value of energy. Okay, it's up here, and your violet color is the one that is closer to the ultraviolet part of the electromagnetic spectrum. So your violet moving to the blue, green, yellow, orange, and finally the red one. So the red one is down here in your electromagnetic spectrum, right before the visible part of the spectrum finishes and the infrared part starts. So infrared, this part in the electromagnetic spectrum contains less energy than the visible part. So your red color contains less energy than the violet color up here. And so the energy, it's increasing as you move from the red one going to the violet one, which means that your wavelength, which is these numbers that I have around this hexagon, that number, it's increasing starting from the violet, moving all the way up to the red one. So this table here we're going to use later, not now. But I want to go over some of the things before we get to find this here. Now the model that we commonly use to represent the atom is the Bohr model, and it's like a planetary system. You have a center, and then you have things orbiting around that center. In the center we have the nucleus, and that nucleus contains the protons plus the neutrons. And then these semicircles, they're actually whole circles, but it's easier just to represent them like that. And in each one, I'm going to have a letter with a number. I'm going to put that as an N3 and 2. And then I have here N1. And this doesn't mean that each atom contains three things, N1, N2, and N3. That's not true. This N, they can go up all the way to 7, and you will see why, and why we can go all the way to 7 later. So N, it's a letter that we use to represent energy. So I'm looking at my model here saying that N1, it's one energy level. Then we move to a second energy level here. I'm using N2. And then we move to a third energy level, and we can continue to add energy levels all the way to 7. So my model here contains the protons and neutrons in the nucleus, and then the electrons are going to be somewhere in those different energy levels, which is the next topic. So just representing like the same type of model in a different type of notation, just a vertical notation, because it's easier for what we're going to be doing next. So I'm using the first line right here as my N1, first energy level. Then we have N2, N3, and N4. And we can continue adding different energy levels. If this is the first energy level, it means that that's the one that is closer to the nucleus of the atom, or closer to the protons and neutrons. Now, energy levels, your energy is increasing as you move up. So the fourth energy level that I'm representing here, it has a higher numerical value of energy, and we're going to have electrons in those different energy levels. So something that is in the first energy level, or an electron that is somewhere in that first energy level, is going to have a lower value of energy associated to it. And the electrons, they can actually, the electrons are dynamic, which means that they are in constant movement. They can actually move between energy levels, or jump from one energy level to a different one. And sometimes when the electrons move from one energy level to a different one, they will require energy. Sometimes the electrons will release energy, and the absorption of energy and the emission of energy, which is releasing energy, those two things are associated with specific jumps of the electrons. So absorption means that your electron is in a low, or in an energy level with a low numerical value of energy, and it will require energy to jump up or to move to an energy level with a higher numerical value. So for example, a transition of an electron in the first energy level that moves from the first one to the third one. Okay, so going up, then it requires energy, so it will have to absorb energy to jump up. So emission means releasing, and an electron will release energy when it's moving from a high energy level to a lower energy level. So going down, the electron will release energy. Now the amount of energy that an electron absorbs and emits, it's proportional. It's in the same magnitude. For example, there's a specific amount of energy for an electron to go from energy level 1 to energy level 2. And for example, if the electron is absorbing 2 units of energy to jump from 1 to 2, that electron will release 2 units of energy to go back from your second energy level to the first one. When something is emitting energy, the electrons, when they emit energy, that energy can be seen as light. And light has a wavelength associated to it, and depending on the value of the wavelength of that light that is being emitted, we can actually observe a color. And you already saw that your colors are associated with wavelengths depending on the value for the energy right there. So this is important because the atoms, they have specific emission spectrum depending on how much energy it's applied to a specific atom. The electron can jump up from a low energy level to a high energy level, and when the electron goes back or relaxes back, it will release or emit energy as a form of light, and that light is associated to a specific color. So I'm going to look at different possible types of transition, and we are going to try to match like a specific color with a specific type of transition. And the way to do that is to try to determine amount of energy associated with each transition, and then use that information to check a wavelength for a specific color. So looking at the given information here, I have 1, 2, 3 different transitions, and I have 3 colors. So you should think about this like you did this experiment. The electrons, they move from a low energy level to a high energy level, and when they're going back down, they're going to emit light. So let's say that you're doing the experiment and that you're observing these 3 colors, and you know that you have 3 transitions, so we can actually match the transition with the color depending on the amount of energy that you can associate to each transition. So first of all, you should look at your numbers here. This is N4 to N1, N3 to N1, and 2 to N1. All of those are emissions because the electrons are moving from an energy level, a higher energy level, to a lower one. So all of them are transitions. So I'm representing my 3 transitions here using arrows from 4 to 1, from 3 to 1, and then from 2 to 1. Now remember that this here represents energy moving up, so increasing as you move up. The actual distance between the energy levels, it's telling you amount of energy. For example, the distance between N1 and N4 is bigger than the distance that you have between N2 and N1. If that distance is bigger, it means that you have a higher numerical value. So for when an electron is moving from the 4th energy level to the first one, it's going to release more energy because you have a larger distance than when the electron is moving from the 2nd energy level to the first one, because you have a smaller distance. So that amount of energy, right, the higher the numerical value for the energy, the shorter the wavelength. Now let's try to do this here. So I'm going to arrange my 3 given colors here from the one with the lowest amount of energy going up to the one with the highest amount of energy associated to it. So I have violet, red, and yellow. And if you don't know them by memory, you can always look at your diagram here. You have the violet with a higher amount of energy, shorter wavelength. And then you have the yellow, and finally the red down here. Okay, so yellow, violet, and red with the lowest. So I'm arranging them from the lowest to the highest, that what increasing. So that will be the red, moving to the yellow. And finally, out of my three colors that are given, the one with the highest value for energy will be the violet one. And now let's do the same thing with my transitions, or organizing my transitions from the one with the lowest amount of energy associated to it all the way to the one with the highest. So the shorter distance will be between N2 and N1 right there, which means that represents the smaller amount of energy. So that should be N2 moving to N1. That's the first transition. Then I have N3 to N1. And finally, the largest distance is when the electron moves from N4 to N1, which means that the bigger the distance, the higher the energy. And the last one should be your N4 going down all the way to N1. So increasing your colors arrange and increasing energy, your transitions arrange about increasing energy too. So when you have a transition, if you have three transitions, this specific three, and you're observing these three colors, the red color should be the one associated with the transition with a smaller amount of energy, because you have a smaller amount of energy associated to the red color. Then we have the yellow, and then finally the violet should be the color that is associated, in this case, with a transition when the electron moves from a fourth energy level down to the first one. So all of these transitions, they are representing emissions, okay? So before something can emit light, it needs to absorb light for the electron to move from one low energy level to a higher one. Okay? So let's check the table that you have right here. You can get all of this information from the diagram. So wavelength absorb, this one here, we can find the numbers 400 to 450. 400 to 450, the color that is being absorbed is the violet one. And you know, because that's the color that you have between those two wavelengths, 400 and 450. Wavelength absorb, color absorb. Now, to find out the color emitted, wavelength emitted, this is what you have to do. If something is absorbing wavelength between 400 and 450, it's going to be emitting wavelength between 550 and 600. Is the one that is opposite to it. Okay? So that color that is between those two wavelengths is the color that is being emitted. So something that is absorbing light with wavelength between 400 and 450 is going to be emitting light with wavelength between 550 and 600. And the color that you can observe in that case is the yellow one. And then I'm going to do the second one, just the color absorbed, and you can fill out the information that is missing, and then you can do the third one. For the second one, 550, 600, that's what it's being absorbed. For 550, 600 is this one right here. So the color that it's being absorbed in that wavelength range is the yellow one. And now you can use that information to find out the one that it's emitted, wavelength for the color that it's being emitted, and then you can do 650 to 700. So I have three problems here, and I will walk you through some things that you should think about when you're trying to solve these three, and you can solve them on your own time. Okay? So this is asking for highest frequency. Okay? So you need to remember the relationship between frequency, wavelength, and energy. Okay? So a high frequency means that you have high energy, means that you have a short value for a wavelength. Okay? And now you have again your different energy levels here, and you have transitions that are representing emissions, all of them, 2 to 1, 4 to 2, 3 to 2, all of them are emissions. So those are arrows pointing down from the second to the first one, from the fourth to the second, from the third to the second, right? All of them pointing down. Now you want to find out the one with the highest frequency associated to it, which means that you can look at the distances to find out value for the, or to predict which one is going to have a higher value for the energy, and you can use that to determine the one with the highest frequency. That's for the first one. Absorption versus emission. Moving up, moving down. So if something is absorbing, it's going from a low energy level to a higher energy level. If something is emitting light, it will be going from a higher energy level to a lower one. Okay, so that's all you need to find out which ones are representing absorptions, which ones are representing emissions. And then the last one, you're trying to organize this for here in increasing wavelength. So increasing wavelength means that you have the shorter going to the longest on the other side. So you have a small value for wavelength starting here, and that numerical value or the wavelength associated to that specific radiation should be increasing to get the longest one on the other side. So you can also arrange specific electromagnetic radiation based on energy or frequency. You can try to arrange this for here in increasing energy or decreasing energy, increasing frequency or decreasing frequency.